Hi everyone, today I'm going to be discussing the new PCB for the Hydro controller version 3.3. As you can see, it's a factory made PCB and it supports both the Terra controller and the Hydro controller. Let's just go over some of the features and the parts required. Starting from left to right, we have the output for a CO2 sensor. We have output for an 8-channel relay, although we're only using 6 of the channels, and that actually leaves 2 spare digital pins. We have an output for a flow rate interrupter that is to be used with the Terra controller to monitor the amount of water being fed to the plants. We also have an LDR sensor that is used to record the light status. By that I mean, has the light successfully turned on, and if so, what time was it on and off. This is really just used for error failover, or warnings rather, so it can be put in the event log. We also have an output for an E-tape. An E-tape is a water measuring device. If you haven't seen an E-tape before, it essentially looks like a ruler, and it's just a resistive track within a diaphragm. So the water pressure compresses the diaphragm together, and the resistive track obviously contacts, and therefore you get a fixed resistance for a given water level. They're very accurate, but they are more expensive than the SR04 ultrasonic distance sensor, and I'll get to why I'm using that later on in the video. We also have an output for a DHT22 and an output for a DS18B20 Dallas temperature sensor. That is to be used for the water temperature, and the DHT22 is to measure the air temperature and air humidity. We also have an Arduino Nano, which is an Atmel v3.3 chip, and we use that to control an RGB LED, a buzzer, the MCP 4151, and also a zero cross module to control 2 AC fans. So that's why there is 2 chips. The code on the v3.3 has to run incredibly fast. It actually runs in about, I believe it's about 15 microseconds each loop, and that's so it can efficiently get the interrupts and cut up the AC waveform. So, carrying on, we also have, as I said, an RGB LED, and that is connected via a MOSFET for each colour, as the RGB LED can draw up to 5 watts, so 5 watts at 5 amps is 5 watts at 5 volts is 1 amp, so that's 333 milliamps per colour, and therefore that exceeds the 100 milliamp rating, absolute rating for the 328p, and that's why it's going through transistors. So yeah, that's the RGB LED and the buzzer. We have an RTC, so that is a RTC 3231, and that is obviously used to keep track of the date and time. We have, as I said earlier on, the SR04 ultrasonic distance sensor. Now, the reason that I have an E-tape and an ultrasonic distance sensor is because the ultrasonic distance sensor, the data is easily corrupted. By that I mean the sound waves can bounce off the surrounding environment and interfere with the readings, so you must have a very sterile environment with no surrounding objects for the ultrasonic distance sensor to work correctly, including ceilings, because it will bounce off the walls and the ceilings and come back, and you'll get mixed readings quite easily. Whereas with the E-tape, as I said, it's a resistive track and it's a consistent reading, so you'll never get a fluctuation with the E-tape, whereas with the SR04, all it takes is you to come over and be in close proximity to the sensor, and you'll interfere with the environmental surroundings. So yeah, not ideal. I did miss the output for the zero cross interrupter. Unfortunately, the header is actually on the back, so we have it there, ground, a VCC ground, zero cross, and PWM for 1 and 2. So that controls 2 fans rated, well, the zero cross modules are rated to 600 watts each, and there's obviously 2 of them, so you can run 2 very large fans. We also have a 4-channel LLC, logic level converter, from 5 volts to 3 volts bidirectional, that allows us to connect our serial to the ESP8266 for Wi-Fi connectivity, so you can view your data online and even control your device online as well. Not all the features, but quite practically all of the features. It's currently being worked on. I'm improving the web page every week. Carrying on, sorry, just got parts moving around. Carrying on, we have an output for an adjustable voltage regulator that is used to supply voltage to the ESP8266 and for the logic level converters for the display, which I'll get to in a minute. So yeah, we have an adjustable voltage regulator with a trim pot there, so I can finally tune it to exactly 3.33 volts. We also here have the outputs for the TDS and pH sensors, and the standard circuitry here. As I said, there is an MCP 4151 connected to the Nano that also connects directly to the pH sensor, replacing the 10K the 10K analog pot, or screw pot, however you'd call it. Essentially the calibration pot on the pH sensor is removed and replaced with a 3-pin male header that allows it to connect to the PCB and be digitally calibrated via the graphical interface. We have our standard MOSFET circuitry here for up to 6 dosing pumps, parastatic pumps, and their standard circuitry, the kickback diodes, the MOSFETs, and the 10K and 220 resistors for switching. We have, as I said, the 2 logic level converters to power the display. Power the display is incorrect. To convert the logic for the display. The display runs via the display is using the SPI protocol for its data, and that is coming in at 5 volts, and the by display variant uses 3.3 volt logic, so again there needs to be a logic level converter in there. I could have used a 10 channel one for here and a 4 channel for over there, but it was just easier to get the same logic level converters, so that's why there's 2 side by side here. We have some standard debugging outputs here, 0 and 5 volts. Allows us to also power any future devices that may be connected. We have the socket here for a standard 6mm 2.1 barrel connector, which is your DC input. We have a header here for 6 sets of analog input, power and ground. Well, it's actually ground, analog input and power. So that powers up to 6 moisture sensors for the Terra controller, if I get this around the right way. So you can connect up to 6 capacitive moisture sensors, which will again be used with the Terra controller. That's not for the Hydro controller. And I believe that is all the components on the board. This is actually already version 2.1 of the PCBs. I've already had 3 other versions made. There's been improvements, and you have to get one to test it to see if the circuitry is absolutely correct and if everything's behaving. Where we're using third-party parts, it makes it rather tricky. So this was one of the original versions here. We've got another version that I'll show in a second, and I originally got the first one gold plated, but obviously where this is still in testing, it was quite expensive, so the next models were not gold plated, where we was still unsure if it was the final design. And there is some changes to already be made in this design as well. Nothing major. The TX and RX for the ESP8266 header is inverted, so this is actually the TX output there, but that's the TX output for the ESP as well, so it's actually going TX to TX at the moment instead of TX to RX. So on the next model the TX and RX pins will be swapped, but all you have to do is just use the standard header, as I am on the controller over here, and it allows you to connect the ESP8266 without a problem. I do currently have 20 of these boards that I'm willing to sell, and I'll show you one working in a second. As I said, this is the same board, so this is the latest model. As I said, there is only a minor issue with the pins for the ESP8266. Other than that, it is completely functional. Here I have all the devices connected up except for the moisture sensor and the zero cross module, because I don't have an AC fan next to me. I don't have any soil plant pots next to me either. This is in my lounge. So I also made a test interface tool for Windows that allows me to quickly test each PCB and ensure that all the third-party components are working. I already know that the circuitry is correct. But but again, where it's third-party components, you need to test it and make sure that they all are operating. So with that in mind, here is the new test interface tool. It supports, as I said, all the features of the PCB, including sending the Wi-Fi data and simulating different modes. Yeah, so I've already got it connected, so let's open up the serial read the COM ports. That's me typing in there. It should be a read-only box, so I would adjust that. And let's open the serial. Cool. Now we can go over a lot of the features very quickly. I have to be quick, so I can actually hear the energy supplies digging up the road because one of the phases is shorted out. All my neighbours have no electricity, so hopefully they don't turn mine off. So we can set, there's no point setting the alarm mode to none, so we'll set it to minor. So this simulates one of the sensor values going slightly out of range, but not over the error margin tolerance. So it's changed from a blue to a yellow blink, and that's every 3 seconds. Very annoying. We can set it to a major warning, which is red once every second. Yeah, even more annoying. So let's set that back to none. We can play a nice, or should I say, we can simulate a touch tone of the display. If you can hear that, yeah. We've got the bi-display R8875 800x480 TFT display connected via SPI, as I said. So we can start that up with a single click. We click here, and it's turned on. And as is tradition, I draw my little yellow smiley face. Yeah. It's always good to see something working correctly, isn't it? We can get the RTC time and date. We can get the DHT air temperature and humidity. We can get the DADAS DS18B20 temperature. Cool. We can get the we can start or stop any of the relays. So we have our relays connected down here. So if we go over here, you can probably hear them. Hold on, start turning back off. We can start a doser. I've only got one on my table at the moment, so let's just start that one. Oh, that was doser pump 6. Helps if I click the correct button. There we go. Don't shake off the table, it's held precariously. We can set the calibration step of the pH sensor. As I said, that's going for an MCP 4151. Cool. Set that, and then we can get the pH sensor value. I've just got in an old bottle of water there. Yep. TDS sensor. The TDS sensor's lead is so short. You can extend it. It's quite literally 50 centimeters long, and yeah, not much use as it is. So I'm just going to have it dangling down there, but it can just, if I get a bottle of water over here, there's some old squash bottle with a bit left in this. It's a bit acidic, but it'll be fine. Just fine. And what we probably expect is some kind of parts per million in that water. So yeah. And as I said, the sensor isolation is there. So if we go over here, they're currently both turned off. Press a click. That was the pH sensor. Let's read the TDS sensor. Yeah. They're turning on and off. That allows us to reduce the sensor interference, though I must say you still cannot have your sensors in absolutely close proximity. There is still a resistance nonetheless for the current to return up the other sensor, and in future models we are going to try and address that further, but it's not a problem if you have your sensors a sensible distance apart. But yes, you do not want your sensors in immediately close proximity. While I had stated in previous videos that you could have your sensors beside each other, after actually examining the voltage travelling back up them, they were actually always interfering, be it marginally, but they were interfering nonetheless. So I now do state, as it is with this current model, that you do not have your sensors in immediately close proximity. If you must do that, then you need to isolate one of the sensors from the other by putting it in some kind of container so that the voltage doesn't leak out from one to the other. Again, this is only if you put them in immediately close proximity, 30 centimeters or so. In reality, they need to be as far apart as possible, as is the same with any other TDS and pH controller on the market. We can calibrate the TDS sensor, and we don't need to do that though because it is calibrated already. We can set the fan 1 speed and fan 2 speed, although as I said I don't actually have one beside me. We can get the CO2 sensor value for the room. It's always 0 for the first reading. It's just like any other sensor, you need to send the first request, and then once you send the first request it will always get a value afterwards. Fine, just fine, yep. No SR4 ultrasonic distance sensor connected. It would have just given me some absolutely odd reading because my room's so cluttered, there's literally stuff everywhere. Yeah, but we could click that, it's probably just going to come out of here something absolutely random because nothing's even connected to it. We can set the E-tape's zero resistance, but the E-tape is actually slightly hanging off the table and bent. The E-tapes must be exactly straight to operate, and I mean exactly straight to operate, because otherwise you're going to bend that resistive track and it is going to touch. So we have our E-tape down there, they're absolutely reliable. I don't really need to show you trying to hold up a glass and sticking it in there. There would just be a number on the screen. But yes, the E-tape does work. All you need to do is make sure it's in no water, set the zero volume resistance of the resistive track. So we could press that right now. It's probably a little bit bent, but it's going to be something like 2,000 or 3,000 ohms. Yeah, and then you fill it up. You put the E-tape in some water up to the maximum line of 32 centimeters. Then you'd say set maxi tip volume, and therefore you set the minimum resistance and maximum resistance, and it just maps out the rest. If I was to set this right now, I'd probably just get some slightly random number. Oh no, that's good. So 2.5 is the minimum reading of an E-tape sensor, and that's actually acceptable because most pumps don't actually drain to the very bottom of the tank, so you always have that residual water at the bottom, or at least I always get it. As I said, we've got an ESP8266 connected. It does have that issue with the RX and TX pins being backwards. I did actually pay an engineer to build all these, or am paying an engineer to build all these PCBs, and they still make these problems, but I suppose we all do. So that wouldn't send any data until I turned on the ESP8266, which is currently off. So if I press this button, on it comes, and that will be starting up and connecting to the Wi-Fi, and then I normally wait 30 seconds, which is what the code does, and it would start sending data. I could show you the PHP panel bit injecting some data, but there really is no point. Just send a little bit, whatever. I'll check on that in a second. I've got the portal closed. There's no point signing into all of that. It would take 5 minutes and I'd have to enter all my details on this camera, so we're not going to do that. So you can set the doser speed. So currently doser 1, if we started it, it was spinning nice and fast, but you know, let's set the speed down to 80%. It's not actually completely linear. The pump would start stalling at about probably 60 or 70%, just because this is the 5mm one, so there's actually quite a lot of current needed to spin the pump. So if we look at it now it's going nice and slow. So we'll turn that back off. We can one of the features of this diagnostic tool is I can set the RTC's date and time to match the PC's time. The code essentially just reads the PC's time and sends it via serial straight to the Mega that sends it via I2C straight to the RTC. So within a millisecond you've sent your time from your PC and its date to the RTC, so none of that old faffing about trying to sync the time with your DS3231 and uploading the sketch and trying to time it or whatever. No. Obviously you can set the time in the Hydro controller GUI, but you should only ever need to do that if the battery's failed or the RTC's failed, because they do not have reverse current protection. All it really takes is you to touch one of those RTC chips and it will fail, and I'm not even exaggerating. I could show you a bowl of them on my table. We'll grab a few in a second, just if you don't believe me. They are the most fragile devices I've ever met. Nonetheless, starting to get carried away there. We can get the moisture sensor values. nothing connected to the analog pins now, so it would quite literally be a random analog reading, somewhat random number, which is just the environmental surroundings, electromagnetic fields being induced and such will give you a random reading from each pin. Yep. We've got the LDR connected somewhere. It's quite literally flopped down and facing the ground, so it's not going to really read anything. And it's got a resistor on there which is calibrated to be used for high pressure sodiums and such. So in other words, it's more sensitive to very bright light than it is to dim light. We can get the flow rate, but I haven't got any plumbing set up over here. But if I was to press that button, it would get the water flow rate over 10 seconds. There's a slight little bug where it will read the state as high and assume it as 1 interrupt, so we'll probably get 0.13 litres. It's going to have to take 10 seconds to read the reading now. So what the code's doing now is it's sent the value and it's going to expect a response within 10 seconds, or exactly 10 seconds, there we go. And yeah, 0.13 litres, and that was just because it says each time it goes high, take a reading and then swap to the low state. And with nothing connected, it thinks it's a high state where it's floating, so it's not actually a bug, it's not pulled low, because there should be something connected by default. But again, that's only for the Terra controller, so you'll never worry about that, unless you've got your flow rate connected. And that is all the initial features of the Hydro controller, and that's the PCB. What can I discuss next? So I suppose some of you want to know if you can buy one. As I said, there has been quite a few developments of different ones over the times. There's all these different models, and they are actually quite expensive to develop. It's not just making a PCB. I need to make a PCB, buy all the components for one, and then one for the engineers, and then I have just my own one anyway. And we need to do that each revision. Whilst obviously I don't need to buy all the parts again that could be removed, we still need to mount all the parts that can't be just SMD'd off. You're never going to be able to remove something that has that many pins at once with a heat gun. And I probably could use the MOSFETs, but again I like to have a sterile testing environment, so I don't like to really reuse stuff. So essentially, just all these components on this board cost £70 or £73, and that means that each revision's cost me about £200 just for each test. So I spent already £600 on testing the PCBs, and we're going to have to get another one made for the future release that fixes the RX and TX pin. And as I say, we're going to try and do some research into this, but from what the engineers are saying, that they're saying that you're always going to get some interference between two sensors. Whether or not that's actually true, but again we're researching that, but nothing's been worked out yet to try and make the sensors be in immediately close proximity. By that I mean literally having them sat side by side and not getting an interfering reading. So yeah, these PCBs, as I said, it's £73 for the components that are mounted on top, and that includes the standoffs, or the standoffs required for the sensors, and it includes the MCP, and it also includes the power cable as well, not the power supply, just the power cable. So essentially everything that I could give to a customer, and they could then just plug in their third-party components. So that's £73 for the parts, but not the PCB itself. The PCB, I get 20 made at a time, because again this is still in production testing stages, and you don't want to go out and buy 100 and find there's a mistake. So they are a bit more expensive to get them a minimal quantity, and there is research and development costs, not just in making the boards, but then paying the engineer to design the boards, and again the testing, and then obviously my research and development, my costs, and obviously the labour of the code itself, and soldering all the parts on. So if I was to sell one of these boards in this state, note in mind this is the old model, so but with all the components mounted nonetheless, £73 for the parts. If you want me to solder them all on, I'd want it to take at least 2 hours to solder all those connections. Note in mind that you have to, some of it's a bit finicky, and you have to solder on all the LLC parts as well. Most of these components have to be soldered. that would be, I think £25 is probably too cheap, but £73, round it up to 100, and then the price of the board itself, I should really only charge, a bit more than what it costs, but because of the research and development and the price of paying the engineers and obviously having to make a profit, really I need to sell these boards for about £75, just a bare board. Otherwise it's going to take me a very long time to start actually paying it all back. In other words, as it is, I'd already have to sell 10 of these at £60 just to make back the cost of the test boards. Then I need to pay off the engineer, and then I need to start making profit. I'm not planning to sell 200 of these over a year to just make the initial cost. I understand that a startup company doesn't make profits in the first year, but no, I don't have that patience. If you want one, it's £80 for the board, bare, and then £73. In fact, here is the parts cost. So there we go. £73.40 for the parts that are mounted on the PCB, plus £80 for the PCB, and then if you wanted me to solder the initial parts on, that'd be £25. That'd be £180 for a board in this condition. Now, the handmade PCBs, I charge exactly £500 or £550 for the handmade PCBs. So if this is costing £180, and then the third party components, all these parts, costs an additional £284, that is still cheaper than the handmade PCB, but obviously of much higher quality. And in actual fact, that is also including the E-tape sensor, that is £40 and was not included prior. And of course these circuit boards have a lot more hardening than the old handmade ones, such as all the MOSFET circuitry here and all the logic level converters for the ESP and all the other resistors to make sure current is being pulled too high. There's obviously also stuff in the back for it as well. So there is a lot of parts to it. So it would be £80 for the PCB itself, £25 for me to mount the components listed here, an additional £73 for the components. So that's £180 for a PCB in that condition, and then you can go out yourself and just buy these components and just fit them. It's nice and easy, no having to worry about any wiring, just solder on the pin headers to the Mega and Pro and stuff and plug them in. As I said, that's either £284 for all the parts listed here, or if you don't want the E-tape, that's £244. So you can actually make the whole thing for 180 plus 240, so that's 380, 424, 424 to 484. Murphy, my dog's gone. He wants some attention. He needs a haircut. Not you two. I've got electrical components here everywhere at the moment. And you, Scruffle Terrier. Uh-oh, he's got the toy. I'm in trouble now. I've given him eye contact. In a second. I'm almost done, buddies. Just wrapping up this video now then. So, yep, so that's the PCB here. I've shown it all working. It's £80 for the current bare PCB, £73 for the components mounted on top. I charge £25 to fit those components, providing you supply them. If I had to get them, there's obviously going to be a bit of delay in handling charges. Let's just say I charge another £5 to go out and get them all myself. And if you want me to include the third party components, as in you'd like me to build one and include those, I will not be liable for any RMAs for third party parts. By that I mean I don't want to be liable for if your third party Mega Pro for instance breaks. I don't want to be responsible and you having to send it back to me and then me repairing it and sending it back to you. So either you supply the components to me and I fit them, or I buy them but am not liable for any RMAs. The circuit board itself, it's not going to fail at all. The only thing that's on there that's slightly electronical is the MOSFET circuitry, but as you can see it's quite literally a diode, a MOSFET and 2 resistors. So I don't see my circuitry failing anytime ever. Whereas with these third party components, as I said, the DHT22 is quite liable to failing if you short circuit it. So if the power and ground is touched on these, they break straight away, or if you took the power to the on the other pins on the board by accident, they'll just instantly break. So yes, if you want one, you can either supply me the components and I'll fit them, and therefore you can send them back if they break, or I can supply them, but I am not liable for RMA, so I need to put that point across. If you'd like a board, or want to inquire more about it, just send me a message. Thanks for watching. Cheers.